iterations, and hallucination. From many aspects of the EDA flow, hallucination from AI are not really that serious, because that is not worse than the engineers on a Friday afternoon. The iteration loops have been a virtual aspect of the EDA flow for decades, ever since gate delays and wire delays become comparable. It becomes necessary to find out if the result of the given logic test is run will yield acceptable timing. Over the years, these problems became worse. It's because one decision can affect many others. The ramifications of the decision may not have been obvious to an individual tools in the flow. Running tools theory led to a big problems, and in the case of the logic synthesis, it became almost impossible to close timing, even with the iteration, because there was no concept of learning in the loop. These multi-factor dependencies were solved by closely thinking decision-making tools, estimators, and a checker into single tools. So the quick checks can be made along with decisions to find out the likelihood that a given choice may end with a bad end result. We are seeing the increased area where this is necessary, as and many of them have interactive feedback loops so that the users can guide tools based on expert knowledge they have. AI has a highly publicized ability to hallucinate. Many of these hallucinations are funny when not in something critical, especially when it comes to generating graphics. One of my hobbies is modeling British railways from around 1950. A while back, I tried to use AI to generate some back scenes. AI fundamentally does not understand the concept of a train as having two flanged wheels and run within a pair of tracks. Some of the images generated had an arbitrary number of rails, and it got highly comical as when a turnarounds were included. Rails went everywhere, some vanishing into thin air, and some trains levitated over them. See how many errors you can detect in the image below. Image created by the DALL-E 3 when asked for a British railway junction from the 1950s. The other day, I was reading a Communications of Acme, May 2025, which had an article by Samuel Greenberg titled Shining a Light on AI Hallucinations, and in it, he said, as words become numeric vectors and their numerical values multiplied by an order of magnitude inside a model, things get fudgy and meanings are blurred. The model is simply like regurgitates words based on a probability. AI hallucinations are a feature of less than a bug, said Damina Anandkumar, a brand professor of the computing and mathematical sciences at the California Institute of Technology, Caltech. As the models are incentivized to produce plausible text rather than a factual text. This is why many people are looking forward to ride in these hallucinations using retriever augmented generation (RAG). So the purpose of these is to fact check what is being generated and to make sure that what is generated is actually plausible. This is beginning to sound very similar to what we have been doing in EDA for a long time. Not that we believe that the EDA tools are hallucinated, they are just not smart enough to know something was going to work, or that an engineer was rather too quick to finish something on a Friday afternoon so they could get an early start on the weekend. Another person said to me that we have when they used AI to help them generate to analog circuit, It came up with a completely new architecture they have they had ever tried before. I'm not sure if someone else had, and the AI had been trained on the alternative architecture, but we could argue whether that was a smart decision made by the tools or hallucination that turned out to be a brilliant. Within EDA, we have learned that everything has to be verified, and thus it would appear that we have a leg up on many other applications of AI. We are so accustomed to verifying everything to the maximum ability possible in the time frame and cost budget, and we have a lot of experience, far from the perfect, about setting priorities on those resources. It may require some rejiggering of verification flows, but it could be done successfully. It could be the RAG and Gen AI being used in EDA development flow. This big stumbling block is that when these techniques have been used within a tool, they have relied on fast estimators, and the functional verification is certainly not fast. As an industry, we demonstrate with new abstract for functionality that they give me a quick sense of validity of decisions that are being made, and not always think of it as requiring a full regression run. We have made progress in using AI and to look at the stimulus set that may provide maximum feedback for a minimum cost, but we should also be able to ascertain the necessary abstraction to validate any idea to a reasonable degree. This is something we don't know how to do today, even though it has been going on for many of the other multi-physics problems with a wider electronics domain. Digital twins and reduce the older models are example of this. In our recent story about the mixed signal systems, several people said that it was important to have a model generator that could spit out the required abstraction for the verification of defined aspect of a design. We need that did all forms of functionality, and it can be done. One example is ARM, which has long had a single golden model for a processor from which several other models are generated. I'm sure it takes longer to generate the master models to begin with, but then we can be certain that all models that are completely aligned with each other, and there is no need to verify every model that is independently created. With the right verification in place, we could allow the AI or hallucination as much as it wants, and maybe it will be provide breaking news that would never have come about otherwise. Given that we have navigation decisions that were made 50 years ago, AI could provide the industry with a much needed architecting phase, and that could bring about the huge performance and power gain we certainly needed. Next article of Brian Barry is RISC-V increased inference. Does the world need another CPU architecture when that no longer reflects the typical workload? Perhaps not, but it may be a bridge to get to where it needs to be. The industry is increasingly talking about benefits brought by the RISC-V architecture, but is it even the right starting point? While it may not be perfect, it may provide the flexibility necessary to move forward gradually. Its computer architecture and software have followed in the footsteps of the processor developed 80 years ago. They aim to solve sequential scalar arithmetic problems using a fundamental technology that could solve any finite problem, provided it had sufficient memory. The chip industry had shown it's reluctant to move away from that approach, particularly in industry that runs software developed 50 years ago. Software paradigms and backward compatibility have a huge influence. It took decades before programming migrated from single processor to a multiprocessor architecture in any meaningful way. And it wasn't using the NVIDIA developed CUDA that application targeting massively parallel processors started to be developed outside of the high layer specialized applications. So why does industry need another CPU architecture when a typical workload for many applications use data flow problems with a small amount of control? The answer lies in the many ways in which the RISC-V architecture can be evolved, and some of these may enable a slow migration rather than attempting to cross a wide chasm. A couple of weeks ago, the RISC-V community held its annual summit in Europe, showcasing the increasing manner in which RISC-V is being used, and its impact is increasingly, particularly in application domains, do not have a lot of legacy software holding it back. RISC-V is no longer just a tiny embedded microcontroller that you are not even aware of that is in your product, said Angela Gallo, CEO of RISC-V internationally. RISC-V has entered a different phase. This is backed up by others. Compared to previous years in Europe, there was much more industry attendance, said Larry Lepid, executive director of the business development and Synopsys. The content was coming more from industry, and that has changed the tenor of a conference. What we are saying is the RISC-V is starting to introduce in the places that we didn't expect it to the 5 years ago. Gallup provided several examples of the significant progress. Infineon said that adopting RISC-V for automotive. He said the European Union is funding a HPC project and funding automotive project. Meta is using it for AI in their accelerator card. And NVIDIA estimated that last year, in 2024, they shipped 1 billion RISC-V cores in their GPUs. Others highlighted the significant advances of RISC-V into cutting-edge processors. It's not only the low end, but processors serving as a coprocessor or accelerator for GPUs in certain segments, said Mohit Wani, principal product manager of Synopsys. NVIDIA gave a presentation where they said they have almost 30 types of the different kinds of functionality across their portfolio, where the RISC-V based cores are doing the job for those 30 plus functionality. So some techniques are business and technical hurdles still must be overcome. Most automotive is increasingly looking into RISC-V, said Roland Jack, design methodology head and for Fraunhofer IIS engineering of the adaptive system division. They have been hesitant because RISC-V is open architecture in the automotive industry, and you always need someone to blame if something goes wrong. This is hard if you do not have a single provider, but a community. Today, they are increasingly looking into RISC-V due to the potential cost reduction, because in the automotive you look for every cent to lower the price. However, you need to have an ecosystem. It's not enough to have the tools that are able to develop your processor, but also the software on the top of that. RISC-V is gaining ground, but it still has a way to go until we have RISC-V processors as the main horse in the automotive area. Not everyone sees this as being highly noteworthy. However, RISC-V is not a solution for AI, not for training, not for inference, said Steve Lottie, Chief Marketing Officer at Quadri. RISC-V is simple, just another control CPU and the same vein as the ARM, x86, MIPS, Extension, and ARC processor. The latter two also provide the designer with the instruction set customization ability similar to and superior to the that of RISC-V. As such, RISC-V offers nothing of a technical nature that is leaps and bounds better than its predecessors. The combine both extreme views require a long-term understanding of the way the industry works. RISC-V the ability to enable AI solutions, said the Venki Narayanan, Senior Director for the System Architecture and Embedded Solution into FPGA division of the Microchip Technology. Instead, it's evolving. The models are evolving, both at the learning and inferencing levels. And there's the various data types and various memory elements, local memory, and to be able to more custom computing in a much faster way. If you look at that, there are various ways of doing it. RISC-V is enabling that with domain-specific architectures. The unique opportunity. It is rare in the chip industry that an application emerges for which there is no legacy software. Nonetheless, that is happened with AI. Moreover, given the extreme rate at which the technology is evolving, no software is likely to become estimated before it again disrupted. This created the perfect environment for continuous evolution and adaptation. With no legacy software to support, you really tend to tailor your processor to workload and leave out some things you don't need, such as rapid. There's still a lot of optimization that can be done at the architecture level. Even at a microarchitecture level, designing a pipeline and a cache set in memory. And that's all before you get to anything else, before you get to the implementation. The free that comes with the RISC-V enables freedom in the architecture. AI accelerator cards can have a huge number of RISC-V cores, every different cores within the same cluster, said RISC-V International Gallo. You can have 100 of little blocks, each of them different RISC-V cores, some dedicated to moving data in out, and some dedicated to the inference itself and the processing. Then you have the concept of the adding custom instruction that allows you have a tensor unit that are very efficient. This is how RISC-V is influencing the architecture of the chips. The while RISC-V licensing as a cost advantage, that's not only a illusion. It goes way beyond that, such as this one. If you look at the way the accelerators connect to a processor, edged through a faster interfaces typically in a memory mapped fashions. From a developer perspective, if you want work done on the accelerator, you send the data and the task information to the accelerator through the interface, and you will wait for the accelerator to send your result back. But the communication is expensive, and it means cause sitting idle. You are wasting 30% of your time spending sending data and getting the result back at one. You can avoid all of that time if you can natively do those particular operations, sending data through your vector pipeline, which then I connect to that accelerator directory. That this kind of the flexibility only exists in the RISC-V world. Qualtrics Lucky is not convinced, or control CPU suffer from the same severe limitations when applied to AI applications, particularly inference applications. He said, CPUs are designed to chase the pointer in the random code. They are not matrix or tensor engines. At best, these CPUs offer vector, multiply, vector computation throughput. They are bound by conventional load store bandwidth bottlenecks. Thus, every approach purporting to use RISC-V to the AI must handle a separate matrix engine, which introduces graph partitioning problems that are Across the heel of the CPU-based approaches. The appropriate innovation to tackle AI is the creation of the architecture that are inherently matrix by matrix or tensor by tensor optimized, and the decreased CPU-centric dependency of memory caching and speculative out-of-order pipelines. RISC-V enables a piece of this, wrapped in a conventional control processor, and some of our members already have a custom tensor instruction set gallo. That is the flexibility of RISC-V. You can develop your custom instruction for your specific workloads, and you can carry the complete cost of the ownership for your custom specification application. There is also value in standardizing and extending the specifications so that we share the cost of maintaining of the compilers and tool change and the libraries. We have vectors, so we are working on matrix, and there will be a different approach to matrix depending on applications use cases. If it's an auxiliary card, if it's an AI IoT application or edge AI, there will be a different ways of implementing matrix acceleration. So with no other candidate on the horizon, you have to make do with what is available. Data flow is very important in AI, and many compute elements that the microchips Narayanan. As the compute requirements have grown, and that needs to be in a more power-efficient way. It's not just the microarchitecture of the instruction, fetch, execute, and write back. It's how you organize the microarchitecture and the data flow. How do you get data in and out? A particularly large amount of data going from one layer to another layer. You can't keep it going and write back in the DDR. With the AI evolved rapidly, there needs to be a lot of flexibility. The types of models that one needs to implement in an efficient manner are growing. So the Niram Ruparelia, 7 leaders for AI and communication and microchips. Transformers as GPUs needs to this what made AI popular, and there are a lot of also set of the models that are a lot of less complex than of transforms. Those also need a higher performance. For example, Classic CNN, RNN, LSTM need the math block architecture, the DSP block architecture to be more amenable to those transformers to those models in order to make performance a lot better. AI is not just one problem, and flexibility remains important. AI have multiple layers. That Narayanan, you have segmentation, object detection, classification, transforms, and all of those use different data types. How are these layers being implemented? How can you do that efficiently? And how do you get the data in and out between the layers? These are questions that you have. That is how the architecture helps you build that. It includes not only the operations but the data. RISC-V has an inherent advantage where you can make custom hardware without violating the ISA specification, said microchips Ruparelia. You can make processing for a specific data type better, be it at the instruction level, be it in with microarchitecture. So you are building a custom computing solution for that class of workload. This flexibility plays a big role in meeting in being agile toward the new data types they are come along and they will be coming along in the near future for the different classes of applications. But the full requirement for a processor to optimize the task of the tomorrow remain unknown. If we are building to a processor for etching inferencing, and it may be a do classification, detection, segmentation, or even some sort of transformers. Said Narayanan, these are fixed layers, and we know the compute elements are designed to be more optimized and work through this workflow. We build computers optimized for the needs of today, but that doesn't mean that it's safe in new layer or new operator types. To something like that, we can't do it. It's just that it's not going to be sufficient as if you designed it made that way. Ecosystem. The ecosystem has been a major obstacle for adoption in some applications area, but steady progress is being made. We upgraded our membership in the Yocto project in a platinum level say yellow. This is a very long message ecosystem. Set yellow. This is a very strong message in the ecosystem. Yocto is the most pervasive embedded Linux distribution. This is the first time to many years to that Yocto project added to a new ISA and a new architecture being made platinum members, being that RISC-V 5 will be on par with the other architecture. Yocto is used not only for embedded Linux, Edge AI, and IoT, but also consumer set-top box TVs and automotive in the infotainment slide. The mobile is catching up. Google has made RISC-V first-class status as far as Android developed is concerned, and said the Wani. Said the software stack that matures that we will see the entry-level application cores in popular segments like mobile laptops and so forth. When enough the leaders step in the back palace, the Red Hat announced that they have a huge developer preview of RHEL for RISC-V. Said Gallup. Fedora is available for RISC-V last January at a FOSDEM in Europe, as Canonical discloses that they have building plans to support the RV823 the profile with Ubuntu. This message that RISC-V is ready for application processors for the standard operating systems. Significant investments are being made. Another interesting project in Europe is their project set Rapidus. This is injection 260 million to 280 billion euros over the next 5 years. That the three key vendors each building chiplets, not just processor IP. One is a general purpose CPU, as one is a vector accelerator, and one is one accelerator. Those chiplets will be integrated. RISC-V with the new chiplet architecture is interesting. Conclusion. RISC-V is not the perfect solution for many applications, especially those related to AI, but it could provide an evolutionary path. In addition, there is nothing else on the horizon that can provide a better alternative. Very few revolutions have succeeded in the semiconductor industry, and by having the open and growing as community of the people who rapidly evolve the definition of what they need today, as they are thinking they might need tomorrow, and with a few of the horizon, they may be able to get to where they ultimately need to be without taking on too much risk. By taking small steps, the ecosystem can keep up and the steady progress is made. Thank you for your time. See you next time.